Hello again with another video related to work and conservation of energy and calculating speed of an object at certain point in a system. Now I have in this example here a very famous a place many of us went through it and experienced the excitement being in a roller coaster. Now, I have a roller coaster car, starts from rest at point A, and I'm asking you what is the speed of the car at point C if the track is frictionless, all right? That's good. That's really great. Now, the word frictionless confirming that this system is really gonna be conserving the energy, so there will be no energy lost. So we assuming it's an a perfect or ideal scenario of a system. Now there are some really valuable information being given in this example, like the starting of this object at point A, it's at rest, so the initial velocity or the velocity at A will be 0. Now I'm targeting to find how much will be the velocity here of this car. So the velocity at C is unknown. We need to find out. Now, because it's a system, the car moving in it, that means the energy will be conserved. So I can say the total energy at position A equal the total energy at position C. Okay, let's fix this one quickly. It's a position C. All right, now usually the mechanical energy, it's a combination of like the gravitational potential energy, the kinetic energy, and in some cases we can add the elastic potential energy, but in this case we don't have any spring, so there is no need to involve that. So for the position A, I will have a combination of the potential energy at position A plus the kinetic energy also at position A, which equal the potential energy at position C plus the kinetic energy at position C. All right, now what is the potential energy at A? It's mg, and the height at A plus half m velocity at A squared. Now here I have the mass, gravity, and the height at C plus half mass and the velocity at position C squared. Excellent. All right, now first of all, I know for sure that there is no velocity at position A, which means the whole kinetic energy at position A will be 0. This is out of the equation. One more thing, I can eliminate in this equation that is the mass. The mass here, it's the common thing between the three terms, or the left and the right side of this equation. So I can simply eliminate the mass. And something you can notice, we didn't give you or mention anything to do with the mass of this car. So you don't need to really get puzzled. What is the mass? No, don't worry. It's the same mass moving in the entire system. So I can eliminate this when the conditions allow that. All right, so let's see what I have left. I have G with the height at A equal gravity acceleration, height C plus half the velocity at C squared. All right, with simple arrangement of this equation, the velocity at C squared will be 2, and I'll take the G as a common factor here, and it will be the height at A minus the height at C. All right, and let's place values. It's a 9.8. Height at A is 12 meter. The height at C, it's already given, it's a 4 meter. Now simply we're just gonna take the square root for the velocity at position C, and we work it out. Let me work it out quickly. Right, looks like it's gonna be 12.5 meter per second. That will be the velocity of this car at position C when it reaches this a little up curvy hill on top of the roller coaster track. Okay, I hope you find this example useful about the conservation of energy, and using a roller coaster as a good example to apply this concept. And we'll see you again with another example. Thank you.